Good evening. Am I audible?
Yes, sir.
Okay, okay, yeah, fine. Thank you. Um, so maybe we can start. It's 5-1 already. So, welcome to live session for the week 11 for the course Introduction to Semiconductor Devices taught by Professor Naresh Kumar Imani. I am Anant Singhal, a PhD student from IIT Jodhpur, and I'll be assisting in solving similar assignment problems that have been given to you in the week 11 assignment, and that will help you conceptualize the problems more clear. And I'll be covering more of the concept part because majorly the last two sessions are now dependent upon these optoelectronic devices and the LED part. So we'll be covering some of the like concepts, and then at the last of this lecture we'll be seeing some of the problems. So it will go like that. So this is the course outline. So as we have already finished almost the all the important part of this code or the aspect of this course, we have in fact covered the short channel effects that were taught in the last class. And I do remember, I guess, there was a doubt regarding the parasitic BJT effect, so I will cover that also in this particular lecture. Maybe I'll take it later in the lecture. Initially I'll be covering this optoelectronic devices, like what are these optoelectronic devices and why do we use this 3 to 5 semiconductors for the case of these devices, and what is direct and indirect band gap. That I guess you already might be knowing it from the initial lectures. And some of the phenomena of optical absorption, what is photodetector and what is solar cell. And there is a concept called open circuit voltage and short circuit current for the solar cells, so that we'll also be seeing, and most of the numerical will be based upon this concept only. So I guess enough of the overview of the course. Yeah, we haven't.
Sir, last time we also missed one numerical. You told we'll discuss it this time.
Okay, what was the numerical? I don't remember.
Uh, a numerical about the
Transfer what?
transfer era for short channel and long channel MOSFETs. A numerical regarding that concept.
You are saying transfer characteristics, something like that.
Yes, sir.
For short channel and long channel MOSFETs. Oh, I get it. I guess it was not transfer. They were output characteristics, if I'm not wrong. I guess
Oh,
you are
yes, sir.
asking about
Forgot.
this.
Output era, yes, sir.
Yeah, yeah. I do remember what was the question. I guess it was something like this, and we need to find the same for. I guess this was given for short channel, if I'm not wrong.
Yes. And the length was scaled to three times.
Yeah, the length was scaled to I guess three something, 3L1, something like that, and we need to find the same for long channel.
Yes. Short
And
channel one is for the L1 and long channel for the
yeah,
3.
so long channel, I guess we did infer that there will be no short channel effects, and it will be something like this. And okay, the thing that we are confused is was VD set, I guess, right?
Yes, sir. VD
Uh,
set.
so VD set,
I
let's
think
say,
short channel should achieve it earlier.
okay, yeah. So uh, this was the actual answer, I guess, if I'm not wrong. We were linking it with something like this, that we will have a smaller VTH for short channel.
So, but according to one of the solutions of last
Hmm.
assignment, uh, the solution mentions that short channel one has lower current than the long channel one.
Short channel has the lower
Lower
current.
current, yeah, lower current than
L-
the long
l-
channel.
Lesser current. Sorry, lesser L you are saying has lesser current.
Yes,
How is it possible? Uh, can you show where is this numerical or where is the
um,
solution?
And just 10 minutes, sir. In assignment 10, we have the fourth question.
Okay, I need to check it. Give me a moment. This year assignment 10.
Yes.
Okay. Okay, so wait. So assignment 10, question 4.
Question 4.
MOSFET 1 is long channel. MOSFET 1 is long. Okay, in figure 4, VD versus ID for two MOSFETs for gate voltage same is given. The W by L for both the MOSFETs is equal. Identify. Okay. So in this case, see, I guess the question was not same in the assignment that you are asking, assignment 10 question 4, they have like specifically said that the W by L ratio is same for both the MOSFETs. They have not shortened or enhanced the length. They are only saying that the W by L is same. So what we can infer from these two, that they might be having a same W by L, and apart from that, the short channel effect will not be having this velocity saturation. So I guess they should be saying MOSFET 2 is short channel, right? Because it is not getting saturated properly. And
So, but if W by L doesn't vary, then how can we classify them as short channel and long channel?
again, see, they have taken two different MOSFETs. You don't think about what is the channel of MOSFET 1 and MOSFET 2. They are saying that a W by L is same, so that you can basically have a fair comparison based upon the voltages of the MOSFET. So let's assume that what they are saying is for, let's say, MOSFET 1, they are saying is W is, let's say, 1 microamps, and let also say, let's say it is 1 microamps. So the W by L is, let's say, 1. And for short channel, let's say, which is M2, if they are taking let's say even a 250 nanometer, then even the W is also 250 nanometer. So the only thing that will be affecting the current, it should not be mobility, it should not be oxide, it should not be WL. It is only based upon this VGS minus VT whole square, and for the short channel, this 1 plus lambda VDS modulation factor will come. And this will not come for the case when you are using what you are using for the long channel MOSFET. Now, the thing that we can discuss is about the VD set, whether it will be lower or higher, but the current level is not a question in this particular problem. It should be a question if they have said particularly that they have changed W or they have changed length to, like, I guess the question that we were doing, they have changed the length, right?
Yes, only the
Yeah,
length was
yeah,
changed. Here, width also is proportionally changed,
yeah.
right?
So that is why we are not concerned about which should have a more current or lesser current, because in that particular case, a same MOSFET has a higher length. But in this case, we have two different MOSFETs, which should be giving some different type of current. We are more interested towards this VD set part. Is it fine? Does it make sense?
Yes, sir. It's clear.
Okay. So again, we should discuss about this VD set. So this was a solution. I don't remember the solution actually. So this is for long channel. This is for short channel. Is this the solution, or it was the opposite way? The VD sat for
So
short.
this is the solution.
Yeah, yeah. So this was a solution, and we were discussing that VD said how it should be higher for a long channel MOSFET. Okay. So since we have a same MOSFET, so let's just play with these equations only. Vaux W by L, and then we have VGS minus VTH whole square. Let's say I'm
Sir,
using.
in the case of short channel, because it achieves critical field earlier
Yeah.
and the velocity saturation also it's attained earlier, that's why maybe the saturation voltage is before that.
Yeah, huh. So that
For
is
the
the point I guess we did discuss, but we were only bothered about this VTH because it will be lower, so it should be having a higher voltage, right? This is what we were discussing in the previous week.
Yes,
But
sir.
yeah, we were not bothered about this gate voltage at all. So this is what you are saying is correct. I guess there was one more question in which was giving out the reason, if I'm not wrong now. I do
Yes, sir. We have
remember.
a
So
creative question in there.
yeah. So for short channel MOSFET, what will happen is we will achieve this critical field earlier. That is true because we have a short channel MOSFET. So this will be achieved earlier because the velocity saturation will take place for the case of the short channel MOSFET, but it will not take place for this case of long channel. And if I like explain in very basic terms, so current is nothing but the charge times velocity. So let's say for short channel, it is nothing but charge times V sat, which is the saturation velocity, and for long channel, it is something Q times VD, which is increasing with respect to the electric field as we are increasing. So this VD is, if you remember, it is mu E. So let's say I'm writing mu E, sorry, so Q times, yeah, mu E. So these two things remain same, and this particular field is for a long channel MOSFET is what we are requiring at a later rate because VSAT is already present in the short channel MOSFET. So what it is doing is it is basically taking the short channel MOSFET earlier into the saturation. I do agree that we will have a smaller threshold voltage, but that is one of the effect of that. But if we talk about the complete VGS minus VT, so if even we are requiring a less VG to turn on that particular MOSFET to turn on the short channel MOSFET. So that is why the case for the short channel should have a smaller VD set as compared to the case for a long channel. And the second thing is you can clearly see this channel length modulation is, I guess it was taking for short channel and it was exactly constant for the long channel. So these are the two things that we need to look for that particular question. Does it make sense? I guess it is fine now.
So why doesn't the long channel MOSFET have channel length modulation?
Why does the long? Okay, so see, we have a very large. So yeah, that is a fine question. But let's say this is a long channel MOSFET, and let's say this is a short channel MOSFET. So you see, even if this depletion region, uh, let's say this is VD, if I'm applying a certain VD such that the depletion region for this N plus is this much long, and if I do the case for this much long, so the L effective that is getting changed is almost L by 2 here. But if I see here, it is the L is almost equals to L effective because this is negligible as compared to this particular change. So that is why the pinch off that is happening almost remains same. So we do not have a such a short L effective so that it is bordered by the channel length modulation. So basically the channel length modulation only occurs in the case of short channel MOSFETs because I guess we discussed that it is one of the short channel effect only such that this L effective have a significant impact because for short channel the depletion width of these source and drain are comparable to the channel length, but it is not the case for the long channel.
Okay, sir. Got it.
Yeah. So what else was there? One was parasitic BRT, right?
Yes, sir.
Maybe I can give you a very quick overview. I guess that will be sufficient. I'm not going very deep into that.
Okay, sir.
Yeah. So we have already studied now a lot about MOSFETs. So we have this VD, we have this oxide, and we have this gate. So in general, this is at ground. This is what we are increasing greater than VTH, and this is the main thing that we are going on increasing the VD. So what happens in a MOSFET? Let's say I am increasing this VD. So this particular diode. So let's say this is body, which is again grounded. So this P-N diode is reverse bias, and as I'm increasing this VD, this is getting more and more reverse bias, and that is mean we have more and more depletion region. So once I'm applying this, what to say, this positive bias, these holes, which are the majority carriers here are holes. So these holes starts to flow from drain to body in a very large quantity. So let's say I'm denoting holes by these empty circles. So what happens is we have a large hole current. And why it is? Because we have the electrons, ample amount of electrons in this n plus, and we have ample amount of electrons, oh sorry, holes in this p. So there is electron hole pair generation, and it is going on continuously. So as we are having this electron hole pair generation and recombination again and again, so what we are having a large hole current. So let's say this electron is colliding with some electron, and then these two electrons are again colliding with these two other electrons, and it is going on like that. So it is increasing. So this is what we call as avalanche multiplication, and this happens at the drain side because what we are increasing is the drain voltage, and due to which we have a very high hole current which is flowing from drain to body of the MOSFET. So let me write it as IDB, which is flowing from drain to body. I'm writing it like that, and this phenomenon is known as impact ionization. And once we have this phenomena, so what do we have in general? Any MOSFET will have its internal resistance and capacitance. We do know that, but if I try to make, so we have this substrate resistance, let's say R sub. Let's say this is the internal body that I was talking about. And what now I'm making is a parasitic BJT. So I'll explain what is this particular thing. So as this whole current increases, this IDB increases. What happens? The effective voltage, because we are supplying more and more current over this. So let's say the voltage at this node I'm denoting as VBI. So this VBI increases. And if you have, so what happens? So we have this BJT. In BJT, the condition if this VBI is greater than or equals to 0.7 volts, it turns on basically. By turning on, I mean that, so let's say this is the emitter of the BJT, this is the collector. So we have a large IE, large emitter current. Once we achieve this particular thing, then this VB becomes greater than that of zero point 0.7. So as this whole current increases, it is basically increasing this body voltage. And once it increases beyond zero point 0.7 volts, so what happens? We have a uncontrolled source current. So you can see we have a large emitter current. Basically, emitter is connected to the source. So emitter is what to say, analogous to source in the MOSFET. The collector is analogous to drain in the MOSFET, and the base of the BJT is analogous to body of the MOSFET. So what I'm basically saying that due to this drain to body current, we have some finite body voltage that is increasing, or that is forward biasing this particular diode. So BJT is nothing but two diodes. So let's say I'm making this. So these two diodes is BJT, and once this diode becomes forward biased, we have a large source current which is flowing, and you can see we already had a channel, now we have more source current flowing. So what I'm now trying to say, if I plot the VD with respect to this IDS, which is a channel current, so in saturation we know it went like this. But now what this BJT has done, it has given it enough source current that even after increasing the VD, let's say this is VD, let's say 10 volt. So let's say at 10 volt, we had a certain current value, which is this particular thing. Let's say this is 1 milliamps. Now at 10 volts, what has happened? You can say this VBI has become forward bias, which is zero point 0.7, and it due to this, it has now become an amplified current. So this source current, which was only 1 milliamps for 10 volts, so let's say it has now become maybe 1.1 milliamps. So in general, what do we need is we need to apply more voltage to get more current, right? But here you can see the current is already there. So we do not require even 10 volts to have that particular voltage right now. So what happens in IDVD? So at 10 volts, what happens is the current tends to increase, but the drain voltage is not required as much as it was the case before. So this is the parasitic BJT action. and this is what we call as snapback behavior. Basically, the snapback, basically the voltage is snapping back instead of increasing like this as it should due to, let's say, impact ionization or something. It should be like this, the current. But ideally, what happens is due to this parasitic VDD turning on, we have more source current already supplied to the channel, and effectively we do not require a large amount of VD, and this things goes back. And this is what we call a snapback, and this happens due to this parasitic VDD which is already present inside the MOSFET. Make sense?
Sir, when there is a increased flow of volts to the body and the body voltage increases,
Yes.
shouldn't we assume some capacitor there? Because how would the body voltage increase without the charge getting stored there?
Yeah. So that is the case. So it is already. So we have CDV, we have CSV. That is for sure. Parasitic capacitances are always there. That I assume that you already know. The current is increasing due to these capacitance only because they are already offering the lower resistance part to increase this VBI. That is fine.
Oh,
Yeah.
why did we consider R sub then?
Sorry.
Why did we consider the substrate resistance?
Yeah, because we like in practical devices, this is the main phenomena. Like if you try to model or write some mathematical equations to control this body voltage, so this is what we consider as the most uh, what to say, most dominant parameter using which we can control this turning on and off of BJT. So this has a finite value in case of a practical MOSFET. So that is why we in general write R sub to denote these things.
Okay, sir.
Yeah, the flow is due to these capacitance only, that I agree, and these capacitance only is basically providing the low resistance part to basically increase the body voltage.
Okay, thank you, sir.
Yeah. So maybe let's move ahead now. Okay. So what was the content? I forgot again. Yeah. So we'll be studying optoelectronic devices. See, these things are not as much important as the previous things that we have already covered because until and unless some particular industry is basically have some expertise in the optoelectronic devices or they want you to do work in the optoelectronic devices, then only it will be considered. But in general, all the industry that are considering giving jobs, they are only basically worried about this MOSFETs and the silicon based MOSFETs. So you should be having all the concepts clear till the part that we have already covered. And yeah, this is just for your overview. Now we'll be studying the first topic, which is optical absorption. Yeah. So basically, we know that when a semiconductor is illuminated with light, that is, we are giving a certain burst of photons. Let's say this is some semiconductor, and we are having some burst of photons on its surface. So I'm giving the energy as h nu that we already studied, I guess, in the initial parts of the this course. So the photons may or may not be absorbed. This we this we can inform, and this is basically based upon two things. One is depending upon the photon energy, which is h nu, and the second thing is band gap of the material. So what I can say is if the photon energy is less than the band gap of the material, so in this case what happens is the light is transmitted through the material and semiconductor basically appears to be transparent. Transmitted through transmitted through the material, and it acts as like a transparent sheet, or you can say something like that. But once you give a energy of photons that is greater than that of band gap, so what can happen? So I can basically make a band diagram. So let's say this is conduction band, this is valence band, this is completely filled with electrons, and this is, let's say, Eg, that is I'm talking about. And if you give an energy which is greater than that of Eg, so this energy can interact with these electrons. And what can happen is, the photon can interact with these valence electrons and elevate the electrons to the conduction band, right? So once this conduction electron comes to the conduction band, so what happens is we have a electron hole pair here, which is in the valence band. Yeah. So what I'm trying to say is, if h nu is greater than Eg, as someone kindly mute yourself, whosoever it is. Yeah. So what I was saying is, if this photon energy is greater than that of the band gap, then the photon will interact with the electrons in the valence band and can elevate this electron to the conduction band. And basically, we know that the going of electron from conduction band to, sorry, valence band to conduction band is basically the conduction, or we have some current flow only when the electron from valence band goes to the conduction band. So, in summary of this thing, what I can write is, if h nu is greater than Eg, electron hole pair is created, and the excess electron or the excess energy may give this electron on hole additional kinetic energy, which will be dissipated. Energy can be dissipated in the form of heat. So this is what we consider with respect to the photons, and we have the criteria which is we call as the intensity of photon. So this is the measure of the energy once we apply or once we throw some photons on the any semiconductor surface. So the intensity of the photon flux is denoted in general by IVX, and it is expressed in terms of energy per centimeter square second. So if we assume that, let's say, at x equals to 0, the IV, that is the intensity, is nothing but IV naught, then the intensity at x is given by IV naught exponential of minus alpha x. Basically, we have the maximum intensity at the starting, which is, let's say, so maybe I can plot it, x, and this is IV. So this is IV naught, and more interaction happens, we have the decrease in the intensity. So that is like very straightforward. So intensity will decrease if you have some exposure to that photon to some material. Here alpha is the absorption coefficient, that is amount of intensity which has been absorbed by the material. And similarly, the power per unit volume, because we know that energy is nothing but power per unit time. So we can relate with this. So power per unit volume, let's say again at a distance x, is given by, let's say, P at x is P naught. It will also get dissipated, where this P naught is nothing but the incident power, which will be maximum, and it is per unit area. The second thing is generation rate of electron hole pair. As I already explained that how this electron hole pair is generated due to this uh, energy having greater than that of band gap. So this intensity IVX, as I already told you, this is nothing but energy per centimeter square per second, right? And this alpha IV is the rate at which energy absorbed per unit volume. So if we assume that one absorbed photon creates one electron hole pair, so what we can write this, that the generation rate is I'm denoting it with G. It is nothing but the alpha IV, which is the rate at which the electron is absorbed per unit volume divided by the energy, the applied energy, h nu. So the unit of G will be, so I guess it is clear. So it will be number of electron hole pairs per unit, because this is energy. So we have energy will cancel out. So it will be per centimeter cube second. This is straightforward again. So let us see a very basic thing. What I was through a numerical we can see. So let's say we have a silicon semiconductor illuminated with the light having wavelength, let's say 1 micrometer. And what we need to find is we need to find the thickness of semiconductor that will absorb 90% of the incident light, or incident photon energy you can say. And alpha I am giving you 10 raised by 2 per centimeter cube. Do you want to try it, or I should directly just solve it? Uh, Kindly let me know if you want to try it.
We'll try it, sir.
Okay, okay, then go ahead. Maybe you can take 2 minutes. This is very easy. Just if you have understood the concept of absorption and emission, then you'll be able to do it. So maybe take 2 3 minutes and let me know the answer. Okay, so let me give some overview. So have you tried? Any guesses? Okay, so what the question is saying, let's say this is a semiconductor. So I've got one answer which is 233 micrometers. So we'll see. So it is saying that at x equals to 0, we have a certain intensity IV naught according to the formula, and at x equals to t, it is asking for the thickness such that 90% of this has been absorbed. So what is left is only 10%. So it is what it is saying is IV naught exponential of minus x. So what I can write is 10% of this IV naught, which will be 0.1. IV naught is nothing but IV naught exponential of minus alpha x, and x is nothing but the thickness. So alpha is it given? It is given. So it is 0.1. So exponential of alpha x is 10. I'm taking log on both the sided. So x is ln 10 by alpha, right? Ln 10 by alpha. So ln 10 by alpha is 10 raised by 2. Ln 10 is 2.333. So it is 0.02303. So this is in okay, everything is in the question is in centimeters. So this is centimeter, and you have given answer in micrometer. So we can convert that. So this is 0.02303 into 10 raised power minus or 10 raised power 4 micrometer, which is 1, 2, 3, 4, 230.3 micrometers. Yeah, so that is correct. I guess you have written the same. Hmm. So this is the correct answer. It's good that you have understood it. So maybe again we can try a very quick question. This was a easy one. So again, what I'm giving you is, let's say we have a gallium arsenide semiconductor. Temperature is 300 Kelvin. Assume that the photon intensity, that is IV, at a point X is 0.05 watt per centimeter square. And the lambda for this particular thing is zero point 0.7 micrometer, 0.75 micrometer. At this wavelength, alpha is given as 0.9 times 10 raised per 4 per centimeter cube, and you need to calculate generation rate. Everything is given basically of electron hole pairs. So I'm denoting electron hole pairs with EHP in this whole lecture. So yeah, so I hope this is again a very easy problem. You can try it out, a direct formula based problem. uh, I think you will try it, right? So I'll wait for 2 minutes. Okay, so let's give it a try. This was, I guess, a more straightforward question than the previous one. So the generation rate is nothing but alpha IVX divided by the energy. So energy is h nu. We can calculate it. So we need to convert it into joules only. So we have this 6.6 times 10 to the minus 34, and we have lambda, which is given by zero point 0.7 micrometer. So I guess it is in centimeter. I need to convert it in centimeter because everything is in centimeter in this particular problem. So this will come out to be, this is 30, 32, 22. Okay, not, let's say this is in meter itself because the final thing will be joules per second only. So I should not write here centimeter because the velocity that I've taken is meters per second. So meter and meter will get cancelled out. This is 28, 820. So this is coming out to be 2.64 times 10 raised to the minus 90. So now generation rate is alpha is given. It should be given. Yeah. 0.9 10 raised to the 4. IVX at this point is 0.05. So now everything is in centimeter. So the final answer will come in per centimeter cube second. And h nu is 2.64 times 10 raised to the minus 19. So we just need to solve this thing. It is 1.7 10 raised to 21. Is it fine? This was straightforward, I guess. Please let me know if it is fine. Then we can move ahead with a better question.
Sir, upon multiplying alpha and IB of x, how did we get the unit as centimeter per centimeter cube second? Could you
Oh,
please clarify that?
yeah, okay, okay. On multiplying, so you are asking about this unit, right?
Yes, sir. Yes.
Yeah, so this is the unit of generation. So this is by energy also. So I did tell you here.
Okay.
So IVX is energy per centimeter square per second. Alpha is, I guess, per centimeter cube. What is alpha?
It's per centimeter cube.
Uh, and this energy is getting cancelled out, and this is now per unit area, so that is why extra, let me write clearly. So this is energy per centimeter square per second, and this alpha is per centimeter cube. How to write this? Let's say this is per centimeter cube multiplied by energy per centimeter square per centimeter second, and this is energy per unit volume. So basically this will be per unit area है क्या? Give me a moment. So this h nu is, should be per centimeter square, energy per unit area. So is this coming out to be what I want?
Yes, sir.
Yeah, I hope you know now. This
Yes.
is per centimeter cube per second. Hmm. So let's try a better question. So like hear the question properly, otherwise you will not be able to solve it. So what I have is, so this is, I guess, a very previous year gate question. I'm not sure. So let's say we have a germanium sample. The dimension of that particular germanium sample is 1 centimeter cross 1 centimeter. It is illuminated with 20 megawatt, sorry, let's say milliwatt, not mega. It is illuminated with 20 milliwatt 600 nanometer laser light as shown. So maybe I can make a diagram. I'm not sure how to make this thing. So this above layer that you see, this above thing is silicon. Maybe I can make it with some different color. Yeah, so this above blue thing is silicon, which is, I guess, completely full. It looks empty. And this below thing is germanium. So what the question is saying that this particular material is illuminated with a 20 milliwatt of energy, 600 nanometer of wavelength, and the area of this thing is 1 centimeter and 1 centimeter. And this is basically, let's say, thickness of germanium is T, and thus sorry, this is SiO2. Thus, thickness of SiO2 is 100 nanometer. So now I'll say the question. We have a germanium sample having dimension 1 cross 1 centimeter square, illuminated with 20 milliwatt 600 nanometer light. The illuminated sample has a 100 nanometer lossless. Lossless means that there will be no energy or loss when the light goes from silicon dioxide to germanium. Lossless SiO2 layer that reflects one fourth, maybe I'll write whole question here, one fourth of the total incident light from the remaining light. One third of one one third of power is reflected from the SiO2 germanium interface. One third is absorbed in the layer, and one third is transmitted. So this is transmitted through other side. I hope you understand the question. So we have germanium SiO2 interface, and we have two different materials which are having 1 centimeter cross 1 centimeter. We have incident 20 milliwatt 600 nanometer of light. This SiO2 reflects one fourth of the total incident light. From the remaining, one third is reflected from this interface, one third is absorbed by this germanium, and one third is coming out through this other side. So let's say the alpha of germanium at 600 nanometer is 3 times 10 raised to power 4 per centimeter, and band gap is 0.66 electron volt. So find the germanium layer thickness. So this is exactly the same question as it was for the first question, and you need to find it in micrometers. Do you understand the question? Any doubts? I can clear it right now, and then you can try. Any doubts in understanding this?
No, sir.
Okay, so maybe you can give it a try. You can take 2-3 minutes, and then I'll solve step by step. Anything?
Not yet, sir.
Okay. Uh, do you want some more time? Maybe.
No, sir. You may.
Yeah, yeah, fine. I'll try to solve side by side. So what the question says that the total incident power is 20 milliwatt. The first thing that the question says is this silicon is lossless and one fourth, sorry, yeah, one fourth, what is happening? Yeah, one fourth of the total is getting reflected. So what we can say is one fourth reflected back, right? So 20 of one fourth is 5 milliwatt. 5 milliwatt is reflected back. So what is remaining is so power incident at germanium SiO2 interface now is nothing but 20 minus 5, that will be 15 megawatts. And out of this 15 megawatts, it is saying the power absorbed by germanium is one third. So 15 one third is 5 milliwatt. So the remaining that we have going on to the surface. So power going to germanium surface is 15 minus 5, which is 10 milliwatt. So this is kind of the incident power that is going on the germanium surface. And power transmitted, it is saying one third. Like other side, the power transmitted to through the germanium, let's say, it is 5, one third of 15, I mean, it is 5 milliwatt. So basically, we have now this germanium incident is 10 milliwatt, coming out is 5 milliwatt. So the formula remains the same. So instead of intensity, we have the power. So P naught alpha x, and at we need to find the thickness. So at T, we know that it is 5 milliwatt. Incident is 10 milliwatt. Exponential of alpha is given. Alpha is given 3 times 10 raised to the power 4 x. So this will be 1 by 2.5. So T will be ln 2 times alpha. Alpha is 3 times 10 raised to the power 4. This will be in centimeter. So what I can write is ln 2 by 3, and this is 10 raised to the power minus 4 centimeter. So this is nothing but micrometer. So the answer will be ln 2 by 3 micrometer. So maybe we can solve this. This is 2.303 by 3 point 721, something like this will come. Is it fine? Ln 2 is 2.303, right? I'm confused. Sorry, ln 2 is not 2.303, ln 10 is that. Ln 2 is 0.693 divided by 3. So it is 0.231 micrometer. Is that fine?
Sir, why didn't we take the power incident on the Germanian surface to be 15?
Okay. 15. Oh, so 15 is at the interface. So that is fine because I guess somewhere it is written. So one third is reflected from SiO2 interface, right? So what we have is we have 20. One fourth is reflected by this SiO2. So we are left with 15, right?
Yes.
And out of that, one third is reflected from the interface. So one third is 5. So 5 is also reflected. So what we are left with 10.
Okay. Okay.
Yeah. and then one third is transmitted through the other side. So 10 is incident and 5 is uh, what to say, transmitted.
Okay, sir. Got it.
Yeah. So this is also a similar problem. You can give it a go quickly. So we have a slab of silicon 5 micrometer thick. We need to determine the percent of photon energy that will pass through the slab if the photon wavelength is this, and alpha is given this, and lambda is also given. So this is straightforward. Um, I is I naught exponential minus alpha x. Thickness is given 5 micrometer. So x is 5 micrometer, which is 5 10 is per minus 4 centimeter. Alpha is given 10 is per 3. So basically we need to find out I by I naught only. Into 100% will be there. So it is exponential of, I guess, 5 into zero point 0.5 minus zero point 0.5. Sorry. I hope I'm not wrong. So exponential of minus zero point 0.5, what is the value? It is 0.606, and you can say it is 60.6%, which is option B. This was straightforward. We need to find the percentage of the photon energy that will pass through. So 60% will pass through, and 40% will be absorbed.
Sir, in the question, absorption coefficient unit has been mentioned to be 1000 per centimeter.
Yeah, yeah,
Shouldn't
yeah,
it
yeah.
be 1000 per
Yes, no, no,
centimeter
no.
square?
Yeah, yeah. So we had a confusion here, I guess. So this was pure energy. So it was -1 only, and this is energy only. So this particular thing is not per unit volume or per centimeter cube. This is core energy. So that is why we were having some confusion here also. So I guess everywhere else I have written per centimeter cube, if you have noticed, except from this. Here I have given alpha as per centimeter cube, see, per centimeter,
Oh, yes, sir.
and here also. So that energy is only electron volt or joule per second, whatever it is. Okay, so let's move ahead. Now this is a simple question of generation. So do you want to give it a try? This is again straightforward. You just need to solve it.
Yes, sir. We'll try.
Okay, fine. So go ahead.
Sir, you are muted.
Yeah, yeah, I have only written the hint. So you can find the G, and the excess ion concentration is G times the lifetime. So you have everything given in the question. Just give it a try. I'll wait for 2 more minutes.
Okay, sir.
Okay, so let me start solving side by side. So it is given that we have gallium arsenide of thickness 10 micrometer, which is 10 is a minus 3 centimeter. Photon intensity is also given. It is 0.05 watt per centimeter square. Lambda is given 793 nanometer. Is incident alpha is also given 10 is for 4 per centimeter, and tau is also given zero point 0.1 microsecond. So let's take it micro only. So we need to find out the steady state excess carrier concentration, which is nothing but generation times the lifetime, and G we have just written it is alpha IV by h nu multiplied by the time constant here. So alpha is 10 is per 4, IV is 0.05, and h nu is okay. So lambda is given, h nu is hc by lambda basically. Okay, so maybe what I can do is, this is in nanometers, this is 0.793 micrometer. And if you remember, this is in electron volt, we write quickly as 1 point, sorry, yeah, by Eg in electron volt. So Eg I can find out, sorry, it is the opposite. Eg in electron volt is, yeah, Eg in electron volt is 1.24 by lambda in micrometer. So 1.24 divided by 0.793, this is 1.56 if I'm not wrong. So I'll write here 1.563 and I should convert it into joules. And what else? The lifetime is zero point 0.1 microsecond, right? So it is 10 to the minus 7. So this will be the answer. This will be 12, 16. What is the options? Okay. Okay, okay. So this will be, I need to solve this. Mm, 12, 16, 16, let's say 14, 5. 5 divided by 1 divided by 1.6. So I'm getting 1.999 and it's for 14. And the unit will be, it is multiplied by time, so per centimeter cube. Is there any option like that? Okay, yeah. So 2 into 10 is per 14, option A is the correct answer. I hope my calculations are correct in terms of power. So kindly cross check that. Is it fine? Okay, so quickly now do this particular question, then we'll move to the next topic, that is solar cell. So this is again a same, not same, but similar problem in which you need to find the whole concentration. So let me quickly go through. So it is saying that the bar of silicon is doped with boron, 10 is per 15 per centimeter cube, and it is exposed to light such that the electron hole pairs are generated. So generation rate is given 10 is per 20 per centimeter cube per second. The recombination lifetime is also given 10 microsecond. The whole concentration it is asking. So the whole concentration total will be P naught, which is the doping, plus the delta P, which are generated by excess pair. And how can you find delta P? Delta P will be equals to delta N. The excess holes will be equals to excess electrons, and G is nothing but delta N by tau. So this is what you have already done in the previous problem. First you need to find delta N, which is G times tau, and then just add the 10 is for 15 with this excess holes. Is it clear what you need to do?
Yes, sir.
Yeah, just do it quickly and let me know what is the answer. So I've got one answer as A. So let me solve it now. Um, so delta n is G, D is alpha IV, alpha is what? Alpha is not given क्या? अच्छा, G is directly given, sorry. 10 raised power 20 is G or 20, yeah, 20, and this is 10 microseconds, so 10 into 10 raised power minus 6, so 5, so this is 15. Yeah, so this will be equals to the excess holes. This was very quick. P naught is also given, right? Hmm. 10 is for 15 plus 10 is for 15. So yeah, this is 2 times 10 is for 15 per centimeter cube. It is fine. So quickly, maybe I can summarize the concept of solar cell and we can do the numerical problems in the next week. This will take some time. Before that, is there any particular lecture before this, like in the previous 10 lectures that you might have faced some difficulties? Because what I'm thinking is in the next week, I'll be taking an extra class for 1 hour in which I'll be talking about all the important questions from all the each of the weeks. So maybe I'll open the PPTs for all different weeks from week 1 to 10 most probably, because that have more important topics. And apart from that, if you have any doubts, that we can also like consider in it in the next week Tuesday session. And the extra session I'll be taking, I guess, on Wednesday for maybe half an hour or so at max. So is there any particular lecture that you might found difficult? Uh, Maybe till the time I'm explaining solar cell, you can think of any particular lecture by seeing the course content. And after this description of solar cell, we'll be discussing about the same. Is it? I hope it is fine. So let's start with solar cell. So solar cell is nothing but it behaves like a battery. I'm trying to explain it in very generic term. It basically supplies electricity without any bias. How come? Because we are having incident energy which is in terms of photons. So let's say this is solar cell. I'm writing it solar cell, and it has some internal resistance, but the energy that it is getting is from some sunlight. So the sources which supplies electricity without any bias are known as photovoltaic. So without any bias is the voltaic part, and photo means due to the supply or due to the sunlight. So a basic solar cell is a PN junction. So what happens is, let's say we have some ECEV, we have this incident energy that I talked about in the initial part. If this H nu is greater than equals to of EG, that means I guess SC by lambda is greater than that of EG. So lambda should be less than, I mean to get the bias, we know that the energy should be greater than that of the band gap. And by solving this, we are getting that the lambda should be less than that of HC by EG, right? So basically for silicon, we know the band gap is nothing but 1.12 electron volts. So we can calculate the lambda 1.24 by 1.1 micrometer. So this will come around 1.2 1 point something 2 micrometer. So what I can say is, if I plot the distribution, so this is how this lambda looks like. So let's say this is energy versus lambda. So let's say this particular point is 1.2 micrometer. So what it is saying that the lambda less than 1.2 micrometers will be absorbed, because that will be, so this particular energy will get absorbed and this will be discarded. And this energy is absorbed. So this is how a solar cell works. So what we can conclude is that all the photons having lambda equals to or less than that of 1.2 micrometer will be absorbed by silicon. And to in fact to harness all the solar energy, we need a semiconductor with a very small energy band gap, because small energy band gap will basically giving us more and more wavelength. So as I said that the basic PN junction, sorry, basic solar cell is a PN junction. So in general structure wise, if I'm talking about, we have something like this. This is the P and this is the N. So we have a very thin P as compared to N, and something like this will be the depletion layer. So I'll let you know why it is more on the N side and not less on the P side. So we have some light incident on this solar cell, and this is the depletion region. So if I try to make the band diagram, so I am again making it like this, cutting by this. Sorry. Yeah. So at this P and N junction, we will be having some depletion region. So this is bulk P, this is bulk N. This we have already discussed, but I'm just, so if we have some incident light, so we have this electrons traveling from here and here easily, because electron travels down the hill easily, and the holes will be going from here to here, and the diffusion length maybe in the P side will be LP, and the N side will be LN. The total depletion width is this thing. So this is a very basic. So photons generated, sorry, not generated, absorbed only in depletion region will contribute to electricity. That we all know. I'm just writing. So let's assume photon falls in depletion region. What happens? It creates a electron hole pair, right? As we know that there is a built-in now, there will be a built-in field due to the barrier potential, or I mean this particular thing, QVBI, that we already know, we write in general. So this field will basically sweep the electron towards the N side, and the holes towards the P side, which will eventually lead to a current flowing, and the junction opposite to the current direction flowing uh, for the forward bias junction. So as I said, these electrons are going here, so the current will be here. The holes are here, so the electron will be here. Sorry, the current will be here. So we will have a certain current flowing due to the electrons going from P side to N side, and N side, the holes going from N side to P side. The photons which are falling in the neutral bulk region, basically the photons which are falling here creates electron hole pairs, but there is no field in the neutral region, as we all know. So there will be no sweep of electrons and holes from these bulk regions. Like this is a very PN junction, very basic explanation of PN junction only. Like there will be acceptor ions here only, and we are not worried about the bulk region of the P and N side. So this is what exactly I'm trying to make here. So basically they will eventually recombine with each other for the bulk case, and there will be no contribution of current because of the bulk region. And what we, as I said, what we do in general, we will try to keep this P very thin P and a very thick N. Why? Because so that very less photon energy is absorbed in the neutral P region, because we are having the photon incident here. And if we have a very thin P region, the most of the energy, photon energies will be absorbed in the neutral P region. Like, sorry, less energy will be absorbed in the neutral P region and the maximum energy will reach to the junction. If we are having something like this, so we should keep it thin. Now, except from keeping thin, because if we have this thin, then the depletion layer can also be a concern, and also the resistance of this thing. I guess you have heard the term sheet resistance. So if we have a very thin, let's say a thin layer of this P, we will have a very high resistance, very high sheet resistance, and once we make some external contact, then lots of voltage will be dropped in the sheet resistance only. And in order to reduce the sheet resistance, what we do is, first of all, we make the P layer very heavily doped. By heavily doping, we are not concerned about having a depletion layer in this particular P thing, and we lightly dope this N so that most of the depletion layer will fall in this. We need to increase the depletion layer somehow so that keeping this P thin and N thick. So the way to do that is heavily doped P so that there is no depletion layer in the P, so that the resistance will be reduced, and a lightly doped N so that the depletion layer will be more towards the N side. So this is a basic representation of a solar cell. If I try to make like this, so we have P, which is heavily doped, and which is lightly doped. Something like this is there. This is a solar cell, and we have the incidence on the P, and the photons, the current will flow like this, and I guess the electrons will move from here to here. So P to N. The main thing is we do not need to apply any bias, because the bias is getting provided by the sunlight. So let me tell you some of the terms now. So let's say this GOP is the optical generation rate. It is similar to G that we were reading of electron hole pairs. So the current due to the photons is Q GOPA, basically per unit volume. So W plus LP plus Ln. So rate of electrons per unit volume into volume multiplied by the charge, because the current is nothing but charge into velocity. So that is why this thing is coming out. And this IPH is the photon current. Uh, and since we know that the junction
Sir,
is
why do we
yeah, yeah.
so why do we make the light incident only on the P side?
No, it is a device like that. We want, like, the solar cell is like this. What we want is, we want a very thin layer like this and like this. So I guess what you're trying to say is, why not NP?
Yeah, why not NP?
Yeah,
Also, wouldn't it be more effective to make the light incident at the interface?
interface means this.
Yeah.
No, we cannot fall a light directly at the interface, right? Because this will act like a, everything will act like a bulk, and here also everything will act like a bulk.
Oh,
For the interface, we have
okay.
this single point, so we need to give it from top only. And the second is, why not NP and PN? That is the question, right?
Yes.
So I guess we can do it like that also. I'm not sure. Let me think. So if we have some incident energy, uh, see, I'm not sure, but I do think that it is doable by taking. See, what we ultimately want is very thin depletion layer on one side and a very large on the other side. So if I take P minus minus and N plus plus, I guess that will also serve the purpose, because again the excess electrons will go from N to P, and the excess holes will go from P to N, and similarly the operation will work. I guess it is
Sir, I
only
still couldn't get why on one side it's made thinner and on the other side depletion is made thicker. The
okay,
reason
okay,
for doing that.
okay, I get it. So what I was saying is that the photons only in the depletion layer will contribute to the electricity, right? So,
Yes.
so let's say if I had something like this and I'm just applying some photons. So what would have happened? After some time, there would have been some depletion layer like this, and only the current that is responsible or that is created by this. But if I try to have the incidence here only, so you can see that they are directly going somehow in the depletion region, not exactly in the depletion region, but they are very close to the depletion region. So that is why we should keep at least one side very thin, and the second side very longer.
Okay, so that the photons do not have to travel to the bulk of the P
Yeah,
material.
because that will have some electron hole pair, right? And that will not contribute at all in the electricity.
Okay, and we do not have any field also in the bulk
Yeah,
region.
yeah. So field is, yeah. So the main thing is we should have something in the depletion region as, okay, it has went away. Sorry. Hmm. Yeah, so that is why a thinner P and a longer, and maybe I'll also give some details why not NP, but I think that NP will also work because again the operation is
Okay.
similar. So I'm not sure, but I'll give you the surety in the next week. So I guess it has went away. So this was the case, W plus Ln plus Lp, and so this was the photon current, and the junction is self biased due to the voltage drop across the load, as we wrote here. So the total current across the junction, which I'm denoting as I total, it is a phonon current, and the basically the junction current, which is, I guess, sorry, this is V junction by Vt minus 1. So this is because of the diode, and plus IPH, which is QGOP W plus LP plus Ln. So what I'm trying to say is, let's say we have a normal PN junction diode. I hope you know that it looks something like this. Sorry, not this. Hmm. So this is a normal PN junction, how it looks. And for a solar cell, what happens is we have something like this. So this is the short circuit current. This is the open circuit voltage. I'll discuss about it also later. So this is ordinary PN junction, and this is solar cell. And solar cell basically works in the fourth quadrant. And we have two components again. So this is due to forward bias PN junction, and this is due to phonon, optical generation basically. Forward bias should be from P to N, and optical generation should be from N to P. Maybe this is fine for now. Well, like very quick summary is the first quadrant. I mean, this can be a theoretical question in somewhere. The first quadrant we have LEDs. I'm talking about IV. The second quadrant we have nothing. In the third quadrant we have photodiode, and in the fourth quadrant we have solar cells. I guess a very old paper has this question that which quadrant is, like, we have a matching question in the gate that which quadrant, which device is following what. So I guess
So
we,
what's the actual difference between a photodiode and a solar cell? Because in both we are shining photons
yeah,
in the
so okay,
semiconductor.
yeah. So give me a moment. For photodiode, I guess I have written somewhere. Mm, uh, okay, so what it is saying is I'm not sure as of now, but the photodiode that we have is always works in the reverse bias as compared to this solar cell, which is working in the forward and reverse bias both. And the photodiode is basically a PN junction diode which is operated in reverse bias. And when an optical signal is incident on the photodiode, the depletion region serves to separate the photo-generated electron-hole pairs and an electric current in the external circuitry. Okay. See, I will cover these photo detector and photodiodes in the next lecture. I'm not sure as of now. Sorry for that. But
Okay, sir.
yeah, I will surely cover this photodiode and photodetector in the next lecture. Right now, I don't have the clarity as of now. So I guess what we are left with is this VOC and ISC. What is this? So that too we can cover in the next lecture if I have a lot of questions here. Okay. So yeah, maybe we can first discuss about that. Then okay, so like for the theoretical part, I guess this is it for today's lecture. But what I want to discuss is, do we have some particular lecture which is having some problems? Week 3 and 5. Okay, so it is the complete message. So let's see what is 3 and 5. Week 3 is thermal motion, electric field, mobility, diffusion, and 5 is PN junction under applied bias. Okay. So is there any particular thing that you are expecting, like, I mean, some particular topic from these also, or all the topics are having equal weightage in, like, from your perspective? Continuity equation. Okay, so continuity equation with, in terms of derivation you are asking, we can cover that. Continuity equation where it is written. Let's see. Okay, it is not written, but yeah, we can add the continuity equation. We will for like in the next lecture. First, we'll cover this photo part only. See, all these things I'm asking about are extra lecture that I'll take on Wednesday. So we can write things so that we can remember in the next week.
So what about the week 12 content?
Yeah, yeah, that will also be covered. Don't worry about that.
Okay, sir.
Actually, we don't have much content in terms of numericals in last 2 weeks because they are both mainly optoelectronics, LEDs, etc. So if you have very basic understanding, then you will be able, like most of the question will be direct and theoretical from those. So that will not take much time. So that is why I'm
Okay,
trying to give more time to the topics that are of more importance.
okay, sir.
So one is continuity equation. The second thing is week 3 and 5 you have suggested. So like first of all, Tuesday next week, maybe I can stop the recording and then we can discuss further. Give me a minute.